A little bit about me. I'm a software engineer at Amazon, and I work on the personalization team, working on recommendations across the retail Amazon website. Prior to Amazon, I obtained my master's degree from the University of Pennsylvania. A lot of the content of today's talk is actually going to be about a little more about the work that I did as a grad student. So natural language understanding is very important, as we all know, whether it's search engines, machine translation, social media, sentiment detection, or even voice understanding. So human language is a rich, varied, and growing source of information, and so it's even more important for us to build scalable techniques for automatic language understanding. But there's a lot of challenges with natural language understanding, especially when we work with text data. We come across multiple words that have the same meanings, like synonyms, words with multiple meanings, like polysemies, some of which are entirely opposite in nature, and then words which behave differently when used as a noun and when used as a verb. Oops. Let me go back. Let's see. So for example, these are two pairs of phrases, hot water and cool water, and hot topic and cool topic. And the relationship between the words hot and cool is going to be different based on the context in which they appear. So words make sense contextually in natural language, which humans can comprehend and distinguish easily, but it's more challenging to be able to automate these tasks. So recognizing various semantic relations between entity pairs and sentences is an important task in natural language processing. So I'll talk about some lexical semantic relations so we understand what are the different types of relations between words that are important. So we have hypernyms like mouse is an animal, we have meronyms like nose is a part of human, and then we have synonyms like happy and joy. And then we also have antonyms that are semantically related but not semantically similar. A lot of this talk will be focused on antonyms specifically, but I'll also talk about algorithms that can help us detect multiple semantic relations and how they can be improved or adapted specifically for the antonym detection task, because learning antonyms automatically is one of the most difficult semantic relation detection tasks as compared to some of the other relations. And I'll also show you why that is. So what are antonyms, right? So in the strictest sense, they are gradable adjectives. Or in a more broader sense, they could include adjectives, nouns, and verbs. There's also there's strongly antonymous words like hot and cold. They're polar antonyms, and then you have semantically contrasting like cold and lukewarm, and then you have words that are not antonymous. They just have another relation between them, or they're not unrelated, like penguin and clown. For the purposes of this task, we'll just say in the broadest sense, any two phrases or any two terms that have opposite meanings or contrasting meanings are antonyms. So the goal of antonym detection is given two phrases, X and Y, or given two terms, derive whether X and Y are antonyms of each other. One of the challenges with this task is that there's not a lot of annotated data for antonyms specifically. So the two main contributions are, first we'll show you how we can learn antonyms using paraphrases and build a large data set that can be used to train a morphology of our neural network for the same task. So learning negations is very important with text data, especially when you have implicit and explicit negations, and you want to be able to identify both types of it. So they prevented us from entering is more implicit negation. We did not enter is more explicit. And then when you want to answer subjective questions like what is the best school for studying computer science? Is gluten bad for you? Do tariffs help or hurt the working class? It's very important to try and identify the semantic relationships between the words when trying to automatically understand the meaning of these sentences. So first I'll talk about a rule-based technique for deriving antonyms from paraphrases. So what are paraphrases? If I had to define them, I'd say phrases expressing the same meaning that are occurring in similar textual contexts, or they have common translations in other languages, which I'll also get into in the next slide. So for example, if you have phrases like not allowed in here, not permitted, they're both two phrases that have equal meanings, and so they can be called paraphrases. So we use PPDB, the paraphrase database. It's an automatically extracted database containing millions of paraphrases. It's available in 22 different languages, has about 100 million word and phrase pairs. It's big and noisy, but it's currently the largest available collection of paraphrases that exist. So how is this paraphrase database created? It's created using a technique that's called bilingual pivoting. What this is that you take phrases in language 1 and you translate them into another language. And if phrase 1 and phrase 2 from language 1 map to the same phrase in language 2, then you can infer that both of the phrases in the first language are probably paraphrases of each other. So in this case, like we have 2 English sentences, and if you take the phrases thrown into jail and imprisoned as 2 phrases in English, and if you translate them to German, they kind of map to the same word. So you can infer that thrown into jail and imprisoned are probably paraphrases in English. So the rule-based technique that I was talking about has a bunch of steps. The first step is creating a seed set using WordNet. So WordNet is like a large lexical English database. It contains nouns, verbs, adjectives, adverbs that are grouped into sets of cognitive synonyms called synset. So it's a manually curated list of antonyms. For example, like direct antonyms from WordNet would be like clean and dirty. That's been manually annotated, but we can make use of synsets, WordNet synsets, to sort of expand that to say if the synsets of dirty are foul and grime, then you can create indirect antonyms like clean and foul and clean and grime to also have an antonymous relation. The second step is to automatically learn antonyms from paraphrases. I talked about what paraphrases were earlier, but there are like 2 different phrases that have like equal meanings. How can we use that to try and identify contrasting or opposite meanings? The simplest thing we could do is we use the paraphrase database to retrieve paraphrase mappings of 2 different types. The first type is where one of the phrases in the paraphrase pair has a negating word, like not. And the second type is where one of the phrases has a negating prefix, like de, un, in, anti, etc. And then, if we apply some sort of morphological analysis to remove the negation factor, for example, if not happy and unhappy are paraphrases of each other because they mean the same thing, but if you remove not, you can say maybe happy and unhappy are no longer paraphrases, but they could be contrasting because we know that the signals that come from the negation feature is indicative of an antonymous relationship. Similarly, if you use negating prefix like unjustifiable and unreasonable, and then you remove the negation prefix from that, you can say justifiable and unreasonable are probably antonyms of each other. And this way we create a large data set. We can expand this even further, just like we did in step 1 by using synsets. So if we got X and Y as antonyms from paraphrases of type not X and Y, then we can also expand XY to say X and synonyms of Y and synonyms of X and Y. And we can get these synonyms using, again, synsets from WordNet or paraphrases from PPDB or any other paraphrase database that you may be using. So for example, here in the previous step, we had from not happy and unhappy, where we're able to derive happy and unhappy as antonyms. And then if we expand that, we can do happy and synsets of unhappy are also contrasting, and synsets of happy and unhappy are also contrasting pairs. And we can do the same thing using paraphrases again, because then they'll have similar meanings. So these are some of the examples of the antonyms that were generated using the rule-based technique. So the first table shows you from WordNet, the direct antonyms are the ones that were manually annotated, and then the indirect antonyms are the ones which we used by expanding using WordNet synsets, expanding the direct antonyms using WordNet synsets. And then the second table down to your left shows examples of where you find paraphrases where one of the phrases has a negating word, and then you're able to derive antonym pairs from it. And then the third table on the right is when you use paraphrases where one of the phrases has a negation prefix, and then you're able to remove it to get an antonym pair using those phrases. So this chart shows you the number of pairs that we were able to derive using this technique. So WordNet direct antonyms is the manually curated list that I was talking about. It only has 3,000 pairs of antonyms, which makes training any type of model on top of it to have good performance in identifying antonyms and distinguishing antonyms from other types of relationships, which is a challenge. And then through the methods that I talked about, by doing an indirect expansion, we're able to create an additional 14,000 pairs. And then using PPDB, where we create pairs of the form XY from not XY, we have 80,000 pairs. And then expand them, we create an additional 35,000 pairs, and then expand them using paraphrases. And then we have an additional 81,000 pairs. So not all of them are antonyms. There's going to be a lot of noise with all of the expansion that we did. So we sampled pairs from this data to do some manual evaluation, and we had about 65% accuracy in comparison with WordNet, which is like 70% accuracy, so it wasn't too bad. So what happened to the pairs after applying all of our techniques were not antonyms? They ended up in 5 different classes. Like they were still paraphrases, or they had an unrelated relationship between them, or they had a categorical relationship or an entailment relationship, or simply some other relationship between the terms, but they're not necessarily contrasting. So using these techniques, we were able to create a massive data set that we could label antonyms as well as other relations and use them in the next step to be able to train a neural network model. So the next step is learning antonyms with the morphology of our neural network. If you're interested in the paper, it's in the speaker resources. I'll talk about some background in the different types of popular techniques that were used for just lexical semantic relation detection. The most popular are path-based and distributional methods, and I'll explain all of these methods in the upcoming slides. And then to improve upon that, there have been integrated neural path-based methods and distributional methods for detecting hypernymy, and that's called HypeNet. And then an improvement over HypeNet was an integrated neural path-based method and distributional method for detecting multiple semantic relations. So if you're able to expand a binary classification from HypeNet to all other lexical relations, and that's LexNet. And so what are distributional approaches? So distributional approaches is where you try to recognize the relation between X and Y based on their separate occurrences in the corpus. Those of you who are in the NLP field probably know what distributional hypothesis is, where we think that the words that occur in similar contexts have similar meanings. And with the popularity of word embeddings in 2013, a lot of distributional approaches would use word embeddings to represent these terms that occur as separate occurrences in the corpus. So one way to do a supervised distributional method is you represent X and Y. X and Y are the two terms that you're trying to learn a relation between. As a feature vector based on the term's embeddings, you could concatenate them. That's one of the simplest ways, but there are many other ways that you could do that. And then you train a classifier to predict whether Y is a relation of X. But this approach does have its limitation. Remember that we were trying to find a relation between X and Y based on their separate occurrences in the corpus. And so they don't actually learn the relation between X and Y, but mostly that Y is a prototypical relation. What that means is, for example, in your data set, if you had cow is an animal as a positive label for hypernym, dog is an animal, cat is an animal, and a lot of those positive examples, the model is likely to learn that anything an animal is a hypernym. Or similarly for a lot of other examples where you have a lot of positive examples, one way to do that is to reverse map it, but it still has its limitations where you're not able to truly understand the relationship between the terms that you're trying to find a relation for, which is to try and classify what is a relation between X and Y. So then we're going to talk about path-based approaches. In a distributional approach, we try to find the relation between X and Y based on their separate occurrences in the corpus. In a path-based approach, you're trying to recognize the relation between X and Y based on their joint occurrences in the corpus. There has been some research back in '92 with Hearst patterns where they came up with patterns between X and Y that might indicate a relation between X and Y. For example, if there were phrases or if there were patterns like X is a Y, they would say it's most likely a hypernym. Neither X nor Y is probably an antonym, and they have many such rules for it. So patterns can be represented using dependency paths in a corpus, and I'll show you how to use this. So in a supervised path-based method, you try to find all the dependency paths between X and Y, the two terms that you're trying to find a relation between. And then you can train a classifier to predict a relation, the most common being a logistic regression. This approach still has its limitations because the feature space is too sparse. You might not always find paths connecting X and Y in your corpus. And also another thing is similar paths actually share no information. You would assume that they have a very similar relationship because of the pattern of the path. So how can we improve this? So HypeNet tried to improve upon the path-based method by trying to create a neural path-based method where they found all the dependency paths connecting X and Y in a corpus, and then they split each path X and Y into edges, and each edge consists of 4 components that are important to try and identify the relation between terms: the lemma, the part-of-speech tag, the dependency label, and as well as the direction of the edge in its dependency tree. And then you would learn embedding vectors for each component, for each edge, and then feed the edges sequentially into an LSTM and use the last output vector as a path embedding. So the LSTM may focus on edges that are more informative or for the classification task while ignoring others. I'll show you what this means. So the LSTM encodes a single path between X and Y and gives you one output vector for that path. But in reality, if you want to find a general relationship between X and Y, two entities X and Y, not necessarily just for a particular sentence, but trying to identify the general relation between X and Y in the corpus, then you could get all the dependency paths connecting X and Y and represent all of its term pair. And then you get a path, an encoder using an LSTM, so you get a path per, you get an output vector per path, and then you can represent a term pair as its average path embeddings. That is, you try to average over all of the vectors for all of the different paths between X and Y in the corpus, and then you could try to classify for hypernym in this specific case, or any other lexical relation if you had a softmax layer that's able to give you a probability across like k different relations. So LexNet did exactly that. They try to improve upon HypeNet, which was a binary classification just for hypernyms, but just try to extend it to classify multiple semantic relations. So the chart that you see here is how well LexNet performed at SemEval. As you can see, it's pretty good at identifying most lexical semantic relations in addition to hypernymy, but it still has a lot of trouble trying to distinguish antonyms and synonyms. And the reason being, it's a combination of distributional as well as path-based methods, and synonyms are not likely to occur together in a path. And antonyms are often confused between synonyms and distributional approaches, most likely because they occur in similar contexts. And this is what the architecture of LexNet looks like. Given that you have two entities, X and Y, that you want to derive a relationship from, relationship between X and Y, what you would do is you would try to get all of the paths connecting X and Y in your corpus, the dependency paths. And then each edge has 4 features: the lemma, part-of-speech tag, dependency label, and direction that I talked about. And for each path, you would encode the sequences of edges into an LSTM, and you get one output vector per path, and then you average pool over all of the different paths connecting X and Y, and then you finally have a softmax layer that's able to classify into one of k different relations, whether it's hypernymy, antonymy, synonymy, or whichever other relation there is between X and Y. But like I said, this was still not very good at trying to distinguish synonyms and antonyms. So I'll talk about an improvement that we can make to this to help it better understand antonyms. So AntNet is a variant of LexNet. It also integrates like morphology of our path features in addition to just the lemma, the part-of-speech tag, the dependency label, and direction. And it's also pretty good at handling multi-word expressions, specifically for the case of antonymy. So the improvement, there was actually 2 improvements to LexNet. One is adding a new feature that says whether x and or y is negated. So x and y are the 2 terms that we're trying to find a relationship between. So we have a new feature that's like either 1 or 0 or 2. One is x is not negated. In that case, y it's negated, or it has a negating prefix or a negating word. And then we use 2 here to show that it's add a new feature to say that y is negated. And for all of the edges in between, we don't really care if they're negated, so we can just give them like an unavailable sort of value for that feature. And the second improvement is once we've identified that either x and or y are negated, instead of using the word embedding for the lemma as it is, but since we know that it's negated, we would try to we record that using a new feature that's negated, and then you try to replace the word embedding of the lemma with its non-negated form. So for example, if you had not happy, instead of using the word embedding for not happy, you would just use the word embedding for happy and then add a new feature that says it's negated. So the replacement of word embeddings was done for a number of reasons. One, you're able to identify rare paths using this technique, because in the corpus, polar antonyms are probably more likely to occur. You might see a sentence like neither happy nor sad more often than you would find a sentence like neither happy nor unhappy. And then you would also be able to identify like seemingly negated words like valuable, invaluable, and also multi-word expressions. Usually the most popular thing to do with embeddings for multi-word expressions is that you try to average over both. If it's a 2-word expression, you try to get the word embeddings for both and then you average over them. The disadvantage of that is if we've got the word embedding of not and the word embedding of happy and we try to average over that, we would actually lose the information that this was actually a negating term. And that's why we try to create a new feature that says that this term is, this phrase or this entity is actually negated, but then instead of using the word embedding for not and happy and then taking an average, we would just use the word embedding of happy. So this is what the AntNet network architecture looks like. It's pretty much very similar to LexNet, except it has an additional feature and it optimizes the embeddings that we use in each edge. And then this could be either a binary classification, that is, it's either an antonym or not, or a multi-classification, where we're able to distinguish antonyms from other types of relations. An integrated model. So we talked about improved path-based methods, but how can we use the strengths of both the distributional approach as well as the path-based approach to try and better learn relationship between entities? As I talked about earlier, using an LSTM, we're able to get one vector, that's the v sub p of xy, that gives you the vector for all the paths connecting x and y across all dependency paths connecting x and y in the corpus. But we try to concatenate that vector with the word embedding for x and the word embedding for y separately, which is the distributional approach, and use the concatenated vector to try and classify for antonymy. So I'll talk about some experiments. We used knowledge resources like Wikipedia dump and computed the paths between the most frequent unigrams, bigrams, and trigrams in Wikipedia based on glove embeddings. So we used pre-trained glove embeddings for this task, and the vocabulary was everything in PPDB that contained the most common 400K words. And the data set is what I talked about earlier in the talk, which we created using the rule-based technique, generated from PPDB, and then so we had about 4,000 pairs. And then the results shows that a combined method, that's the integrated method where we try to combine both the path-based as well as the distributional approach, did better than just the path-based approach for detecting antonymy, both for binary classification as well as multi-class classification. And you can also see that the binary classification was a little bit better than multi-class classification, most likely due to the imbalance, most likely due to the fewer number of classes, examples per class. So we'll talk about the effect of the negation marking feature by comparing their F1 scores. So LexNet is the first one that I showed you in this talk, which used the features, the lemma, part-of-speech tag, the dependency, and direction. And what happens if we just add a new feature, that is to say if the term is actually negated or not? We improve the F1 square just a little bit. And then when we replace the word embedding of the lemma by its non-negating form, when it's actually negated, we can improve it just a little bit more. We also tried replacing the direction feature with the distance feature, that is the distance between the nodes in the dependency path, but it didn't perform as well as using the direction feature. So evaluation against some baselines, we use the majority class baseline that is trying to classify it in the most frequently occurring class in the training data set, and then a distributional approach, and then comparing it with LexNet as well as AntNet. You could see that AntNet performed the best. Since you're almost out of talk, I'm just going to skip through these slides. You can see through the confusion matrix that it did pretty well in trying to distinguish antonyms from other relations. And even in the cases where it was not, it was most likely in some sense an antonym, like polite and sassy, black and white, but they were just classified as not antonyms. You can find the artifacts. It's also on the Speaker resources. And improvements can be like trying to use pre-trained models like BERT-based models that show that you don't need to do a lot of feature engineering and are still able to do pretty well on the SEM-eval task, better than like CNN or LSTM methods. Right, thank you. I'll be here if you want more questions.